A warm welcome to the 28th session of the third module of Signals and Systems. In this session, we will continue with the discussion which we had commenced upon in the previous session, namely to think of a practical system involving speech processing, which took speech as a continuous time input, generated speech samples at the rate of 10 kilosamples per second or 10,000 samples per second, processed those speech samples in a particular manner that we desire, generated a stream of output samples which we called an output sequence, and then reconstructed speech. So, I told you that the process of going from continuous time speech to the input sequence is simple. Use a speech recording device. It would essentially give you a stream of analog samples. We saw one philosophy to move from analog samples to a discrete representation or a digital representation. So, in fact, I gave you what was the concept behind one of the analog digital converters that are commonly used, and then we assume that this stream of bits, the digital word corresponding to that sample, is stored at the appropriate location in memory. So, you have the sequence of samples there. Now, you could subject that sequence of samples to some discrete time processing. It would generate an output stream, an output sequence, and each output sequence point, each sample of the output sequence would again be a digital word. So, in fact, one can reconstruct the analog value from the digital word using again a combination of resistances and voltage sources, what is called a voltage combiner. So essentially you could have some fixed voltage sources which are in relative values of powers of 2. So, I will tell you the principle. So, the actual circuit is a different issue. So, what would be the principle? The principle is use a number of resistors, and this is not too difficult to understand. We can also understand it with the electricity that we do in high school. So, you have a system here where you give inputs on one side of the resistance which are either 5 volts or 0 volts in magnitude. They are all direct DC inputs. You join all the other output points of the resistor together and then connect it to one resistor across which we look at the net voltage. So, this point is connected to 0 volts always. Now, you could take these resistance values as I have written here in powers of 2. So, for example, if you had just 4 of them, you could make the resistance values some R0, 2 times R0, 4 times R0 and 8 times R0, and this is RL here. Just to take an example, these R0 values could be in kilo ohms. So, R0 could be 1 kilo ohm, for example. So, that would make 1 kilo ohm, 2 kilo ohms, 4 kilo ohms and 8 kilo ohms, and RL could be maybe say 5 kilo ohms or 10, anything. I mean, it depends on what kind of currents we are willing to bear. Now, let us write the Kirchhoff's current law at this point, and let us call these voltages here. So, they are either 5 volts or 0. Let us call this voltage say V0, V1, V2 and V3, and the net voltage is V net. Let us write down the Kirchhoff's current law. It says that the net voltage as seen here would obey that the sum of currents coming in here must be 0. What does that say? That tells us V3 minus VL or V net rather by 8 R0, that is the current. So, let me keep showing you one current after another. So, in fact, let us write down the current names as well, that will make it easier. Let us call this current I3, similarly I2, and let us call this current IL. Let us write an expression for all of them, one after the other. So, this is I3 here. Similarly, I2, I1 and I0. And IL is of course V net by RL. And from Kirchhoff's current law, IL must be the sum of all the others. All the others come in and IL goes out. So, that leaves us with V net by RL is V3 minus V net by 8R0 and plus and so on. And all that we need to do now is to rearrange a few terms. Let us do that. Let us rearrange the terms. Now, let us give this whole, let us simplify, let us call this whole thing here, this big expression, let us call it GL1. G stands for conductance, the reciprocal of resistance. And let us denote 1 by R0 as G0. So, what are we saying? We are saying V net is equal to G0 by GL1 into 1 by 8 times V3, and this can continue. So, you notice that V net has a combination of 4 terms. It is proportional to a sum of 1 by 8 times V3 plus 1 by 4 times V2 plus 1 by 2 times V1 plus V0. So, V0 is being given the most significance, V1 is being given half that significance, V2 1/4 and V3 1/8. So, you could think of V0 as being the most significant bit here and V1, V2 and V3 in decreasing order of significance. So I wanted to put a concrete example of what principle could be used, a simple structure. Now, if you have not quite understood, suppose you are not familiar with even these basic electrical circuits, do not worry too much about it. But I thought many people might be familiar with simple resistance calculations, and therefore, I put this example down. So, you get a concrete feel of how we can do digital to analog conversion. Anyway, it is important that we get a link to the physical reality. What are we doing? We are doing all these things abstractly. What are we doing in the physical domain? What are we doing actually on the ground? It is a good idea sometimes to be aware of that. Anyway, so now you have a mechanism, of course, so you will get a voltage which is proportional to the word that you have created, and that voltage can then of course be converted back to speech. We know how to do that. By a player, you could use some kind of a device that converts voltage, you know that, I mean, that is not a play, essentially a speaker. I mean, in a way, after all, something that converts a voltage to speech is a part of so many of the audio devices that we have at home. We do not have too much of difficulty in visualizing those parts, but let us not go into all the electronic circuitry there. Now, what is important here is that the discrete system that we have in between can do a lot of things in a very simple way. And let me start with a very simple example here. Let us take a very simple discrete system which would do something interesting. And before we do that, we must now build some conventions in our expression for the discrete system. So, let us agree on a few things for the discrete system. So, let us look at the discrete processing system and let us build a few conventions for this. We need to put down certain things that will make our system universal, otherwise each time we have a different sampling rate, we have to start writing different symbols. So, let us agree on a few things for all the discrete systems that we are going to build. Let us agree that we shall use the unit time equal to the sample interval. So, that means between whatever be that sample interval, it could be 1 millisecond, it could be 0.1 millisecond, we will agree that we treat that as our unit all along the discrete processing. As a consequence, the sampling frequency becomes the reciprocal of this. On the frequency axis, we think of frequency equal to 1 as the sampling frequency. The unit of frequency also becomes 1 now. And having agreed to this, the maximum frequency component that can be present in the signal before sampling is half now. In fact, it should be less than half, to be very precise. And why do we want this? We want this to avoid aliasing, to obey the Nyquist principle. Otherwise, those aliases, the copies would start polluting the original spectrum. Now, this is in what is called, so this is called the normalized cycles per second frequency, or it is the actual cycles per second frequency divided by the actual sampling frequency. So, it is called normalized to the sampling frequency. But then you can also have a normalized angular frequency, and that normalized angular frequency is 2 pi times the normalized cycles per second frequency. So, therefore, the maximum normalized angular frequency component which we can have in the signal should be less than 2 pi into half, which is pi. Now, let us get the picture clear. Let us draw a picture to understand what we are saying. We are saying that you had this original signal spectrum. In the case of speech, it went, say, from -4 to 4, and you have sampled it at 10 kilohertz. So, you got this spectrum and so on. Now, what we are saying is that the normalized frequency, this is of course the actual cycles per second frequency in kilohertz. And let me write the corresponding normalized angular frequency in red. So, at 5 we would have pi. At 4 therefore, it becomes 0.8 pi. This corresponds to 2 pi and so on. Now, we will have to see more of this in the next session. Thank you.